All right, so next let's take a look at an algorithm for searching the linked list. And this is going to be pretty much exactly like what we saw with a singular linked list. So we're going to have a find algorithm, and you could do your traversal from either direction. You could start from the head pointer and do a linear search. That's all this is, from the head node forward, or we could start it from the tail node and work our way back. You could do it either way. So what we're going to do, just to be a little bit different than the linked list algorithm, is we're going to do our search from the tail and move backwards. So we're going to have to find some value. So we'll call that value little t. And so our algorithm is going to need to have access to the tail reference and the value that we're searching for. So we've got a couple different scenarios. We've got scenario 1 where it's an empty list, and we've got scenario 2 where it's a non-empty list. So in scenario 2, we will have something that maybe looks like this. So let us say that the t that we're looking for is right there. So what we're going to do is we're going to use ourselves a temporary reference, which we'll call P, because we can't be doing traversal with our T reference, because by the time the traversal is over, it would no longer have the memory address of the last node anymore. It would have the memory address of wherever the traversal ended. So we've got to make sure that our tail and our head references don't change when we're doing a search like this. So we're going to set P to our tail reference. So the contents of tail is going to be pointing to P. And then what we're going to do is we're going to go node by node searching for our target. So while P does not equal what? Well, if it goes through the entire list and doesn't find a match, then eventually, if we traverse the whole thing, P is going to contain null. So while P is not null, we're going to continue doing things. So long as P is actually referring to a node, we're going to do something. What are we going to do? We're going to check the contents of that node. So we'll check it. We'll say if p.x, I remember that's what we named our variable when we first started this discussion, if that equals our target. If it does, then we found what we're looking for. So we'll simply return true. True. It is true that this value exists in the list. If not, then we will advance our p pointer in the backwards direction, right? So we'll update it with the contents of the prev reference. We'll update our p reference with the contents of the prev reference, which will move our p one node back. Okay, so if we go through that entire thing and we get to the end, then we never had a chance to return true, which means we never found what we were looking for. So we will return false. Okay, so let's check our two scenarios. Let's trace through our algorithm here. So first scenario, we set P to T. So we copy the contents of T into P. Well, what's the contents of T? Null. So we look like this. So first thing in our find algorithm was setting that P. Now we're going to move to the while loop. Well, P not null. Well, that's false for scenario 1 because P contains null. So the entire while loop gets skipped and we return false. We didn't find it. It makes perfect sense. You're not going to find a value in an empty list. So that checks out. Now, what about our second scenario? Our T that we're looking for is right there. So first thing we do, we set up our P to the contents of T. So P now has the memory address of the tail node. So both P and T are referring to the same node. While P not null, that is true because it's got the memory address of that tail node. We're going to check the contents. Now, does that node's X contain our target T? No. So we're not going to return, and we're going to update the contents of our P reference with the node's prev reference that P is referring to. So we're going to overwrite the contents of P with that node's prev reference. So that's going to change our picture to look like this. And then we go to the top of the loop. Is P not null? True. So check the contents of that node. Is it equal to our target? No. So we're not going to return, and we're going to update the contents of our P with the node's prev pointer that P is referring to. So that's going to advance our P reference to the next node, right? So we go to the top of the loop. Is P not null? True. Does that node's X contain our target? Yes. So what do? We return true. It's found. Fantastic. Done. Now, what if, imagine if none of the nodes had our target value? Well, then this would have evaluated P.x equals T, would have evaluated a false. We would have updated our P reference again, just like before. We would have went to the next node. We'd go to the top of the loop. Is P not null? True. Does that node's X variable contain our target? Nope. So then we would be updating P equals P.prev. We'd be updating our reference one more time. And now it would contain null. So we go to the top of our loop. Well, P not null is false. So the loop's over. and then we go down and we return our false. So it works. It works when we have an empty list. It works when we have the target value we're searching for in the list, and it also works when our target value is not in the list. So success. So both scenarios check out. Our algorithm handles all of it. Now, what is our performance here? Let's do some analysis. So we've got one operation there for assigning our tail reference to our P reference. We've got this test right here. Now, how many times is that test going to occur? Well, it has to occur for every single node, right? So it's going to happen n times. Now, what about everything inside of here? Well, in the worst case, where we have to go through every iteration, we have to do this operation and we have to do this operation. So all of those operations are going to happen 2n times, right? Now, if we don't find what we're looking for, we actually have to do this test one more time because we end up pointing at null. So it's 2n plus 1. And then finally, since we didn't find what we're looking for, we have to return false, right? So those are all of our operations. So we've got 2n plus 1, 2, 3. That's our actual big O. Now here's the thing though, as n gets really large, say infinity, well, what's 2 times infinity? 2 times infinity plus 3 kind of doesn't matter. When you have numbers that large, the plus 3, we can just forget about it. Now 2 times infinity is still infinity, so we can get rid of this as well. So our final performance of this is big O of n. So it's a linear time algorithm.